So today we are going to discuss double integrals in polar coordinate system. I mean that we need sometimes when we need to calculate double integrals, it turns out that it's not enough to know these two templates, which are in Cartesian coordinate system, which we called templates 2a and 2b in our last tutorial. So sometimes it's absolutely necessary to be able to do this in the polar coordinate system as well, unfortunately. So the topic of this tutorial is double integrals in polar coordinate system. So this is only the beginning of tutorial 9. So it's only part 1. So we start out with introduction. Small introduction as to why. Why do we need this polar coordinate system? Why? What all this hustle about? I need to convince you first. To this end, let's consider example 1. Example 1, where we are given a double integral over the region D, as usual, and unknown function f of x, y, dx, dy. It means that we are not going to calculate our repeated integral once we made this transition. We are only going to concentrate on how this transition should be done. Okay, and the region of integration is bounded by this circle. X squared by y squared is equal to 4. Nothing bad about circles. Circles are actually very beautiful curves. Let's plot the curve. And this is circle of radius 2, if you remember. And so it means that this is our area. And of course, as usual, if we try to squeeze this region between two vertical lines, this is our first approach. Let's do it. So this is my first vertical line, and this is the second vertical line. So these are our A and B. So we can explicitly see that we actually have two boundaries. This is the upper boundary as usual. Let it be the green one. And this is the lower boundary, which corresponds to the lowest to the bottom half of the circle, if I may so. So the question arises how to write the equations of both these green and red curves. Let's consider our equation of our circle. We need to express y in terms of x, that is why y squared first is equal to 4 minus x squared. But when you start expressing y itself, you realize that you need to put plus minus here in front. Plus minus in front of this square root. So, and it's pretty obvious, I hope, for you, that plus sign corresponds to the region, to the segment of the circle where y is positive. That is why it corresponds to the top half of the circle. So this equation is y is equal to square root of this expression. And as for the red half of the circle, the bottom half of the circle, of course, it corresponds to a y being negative, of course, because this is in the region where y is negative. That is why the equation of the lower circle is minus square root of the same expression. So it seems like we have no problems of transitioning into a repeated integral. Let's denote this integral I as usual, because I'm sort of lazy to repeat it. And so I'd better write it here. So as our region is squeezed between two vertical lines, it means that we need to start with dx. Dx is from -2 to 2 as usual. And as for the second integral, it's from the lower, from the bottom part of our circle, which is minus, has a minus in front of square root, and to the upper, to the top half of the circle, which has plus in front of the square root. That's it. So that's it. So you might ask me, what the problem there? That it doesn't seem like we had any difficulty writing down this repeated integral. But you know what? The difficulty lies in integration process. When these terrible square roots are involved in your calculations, it means that the integral will be super hard. You have to be a real expert in integration. You have to know so many tricks as to how to integrate. That is why it's better not to do it. That is why So the conclusion is that maybe circles are not such good curves when it comes to transitioning to repeated integrals. Let's consider even more difficult example. This was relatively easy because this is a very nice circle. It has this form. The equation of the circle has this form. It means that the center of the circle is in the origin 0, 0. And this was relatively easy. Let's consider even more difficult example. So it's going to be example 2. Example 2. Again, I'm giving you a double integral with a known function. So integral, double integral over region D. Function is unknown. Again, that's because I'm not going to calculate this integral. I have some difficulty with blurred image now. Okay, where region D, this time region D is bounded by this circle, x minus 3 squared plus y squared is equal to 9. Actually, the region could be written in the form of inequality. It means that sketch the region, shape the region which is inside this circle. If you can see, sometimes the regions can be given in the form of inequality. Okay, so what is this circle? This circle has the center being shifted a little bit. The center of this circle is in point 30. 30. So 1, 2, 3, it's somewhere here. And the radius is 3 as well. So our region looks something like this. So again, we are dealing with this circle. And let's try to make this transition to the repeated integrals again, just like in the previous case. Okay, let's try it out. So let's do it using both methods, just for revision, just for realizing that there's no option at all for us as to make this transition to polar coordinate system eventually. But okay, so first approach is to squeeze your region in between two vertical lines. These vertical lines are obviously 0 and 6, because 3 by 3 is 6. Here, I'm not going to sketch any colors here because I'm reserving them for the second method. Okay, so we're starting by dx. Dx goes from 0 to 6, pretty obviously. And then we need to write our integral from the bottom half of the circle to the upper part of the circle. To this end, we need to express a y in terms of x from this equation. So let's start with y squared. Y squared is equal to 9 minus x minus 3 squared. And the convention is, you know what, you need to simplify the right-hand side of this. If you perform this multiplication, you will see that 9 and 9 get cancelled out. So you will be left with the expression like minus x squared plus 6x. And finally, y is equal to plus minus. It's better to rewrite this in this form. This expression, very unusual, very scary, I would say. And again, just like in the previous example, you know that the top part of the top half of the circle corresponds to plus sign, and the bottom half corresponds to minus sign. So let's use this color coding again. So this is minus this expression, and this is plus the same expression, plus square root of the same expression. So again, we didn't have difficulty transitioning to the repeated integral, but fortunately, we are not given this function, because otherwise we will find ourselves in a real difficulty when it comes to integrating. But let's do this in another order. Let's reverse the order, just for the sake of practicing, and just for the sake of realizing that it's in both methods, in both approaches, it's absolutely impossible to deal with these integrals. It is possible, but only maybe for professionals. They're very tough. So let's recall the second approach. According to the second approach, you need to squeeze this region in between two horizontal lines this time. What are they? Of course, this is minus 3 and 3 because it's the radius of our circle. So we start writing with dy from minus 3 to plus 3. And in this case, what about the left boundary and the right boundary? The left boundary will be the left half of the circle this time. And the right boundary will be accordingly the right half of the circle, And you know the convention. In this case, you need to rewrite your equation, the equation of our circle, expressing x in terms of other variables. So let's do it somewhere. Example here, we can do it here. So x minus 3, maybe I don't have enough room. Oh, I can use this one. I'm not going to write too much here. So x minus 3 squared is equal to 9 minus y squared. Then we can express x minus 3. X minus 3 will be plus minus square root of 9 minus y squared. And finally, we can write that x squared 3 plus minus square root of this expression. As you can see, this equation looks quite daunting, but what can you do? That's the purpose, the whole purpose of doing this exercise. I'm trying to convince you that it's absolutely impossible to deal with circles in the Cartesian coordinate system. But nevertheless, let's push on. Let's finish this task. So you know what? As for the sign, when you need to write the equation of the left half of the circle, it corresponds to minus. So let's write 3 minus square root. So the idea is the same as in the previous case when you express y in terms of x. And as for right half of the circle, it corresponds to the same equation, but with the sign plus in front. 3 plus square root of the same expression. As you can see, in this case, our integral looks even more terrible, more daunting. So hopefully I managed to convince you that it's absolutely impossible to deal with circles, with regions composed of circles in the Cartesian system of coordinate. But you know, at the same time, we killed two birds with one stone. At the same time, you know now how to express y and x from the circle. You need to take into account this plus minus sign all the time. And now you know the geometrical meaning of this plus and minus sign in front of the square root. Okay, so hopefully it was quite useful, but you know, to reinforce your knowledge and your understanding, I suggest you should do this little homework as usually. So this is your homework consisting of only one region, only one problem. So you're given double integral here with a known function as well. And the region is bounded by this circle, shifted circle. And your assignment is to convert this double integral to repeat it using both methods, just for the sake of this exercise, as I said before. So pause your video, do this homework, and here are the answers. Here are answers. Okay. Okay, now we can switch to our next topic. So now you are, hopefully you're convinced that we desperately need polar coordinate system. But before trying to convert double integrals into repeated integrals, we need to get familiarized with polar coordinate systems. So let it be our second topic, polar coordinate system. Polar coordinate system. Polar coordinate system. Polar coordinate system. We need to get used to it first. We need to be able to rewrite our equations in the polar coordinate system. That is why we need this topic number 2, introductory topic, of course. It's blurry. I don't know what to do with this camera. Now it seems better. It's fluctuating all the time. Okay, what is polar coordinate system? Let's draw our Cartesian coordinate system first with x and y axis. And let's consider some point M. Point M has two coordinates x and y. What is the geometrical meaning of these points, of these coordinates x and y? X and y. It means that you know the idea, x is this length and y is here. You know it pretty well. What about polar coordinate system? What changes? It means that to locate, to give the location of the point on the plane, you can use, instead of x and y, you can use quite different values, but you still need two of these values. Let's consider this segment. So this, in polar coordinate system, you don't have x and y axes anymore. You only have origin, which is called pole now. It's not origin anymore, it's called pole. Hence the name, polar coordinate system. And this distance from the pole to your point is denoted by r, Greek letter or Greek, not R, but Greek letter rho. I prefer to write rho instead of R because my handwriting is very bad. When I try to write R, it more looks like 2 or something else. This is why, not to confuse you, I decided to use my favorite Greek letter rho. Okay, so, and this is called polar radius. So O, it's not origin anymore in polar coordinate system, and this distance is called mm, polar radius. And this angle between x-axis and the polar radius is denoted like phi, or maybe some other letter, it doesn't matter, and it's called polar angle. So polar angle and polar radius are two coordinates which represent polar coordinate system. Phi, polar angle, and rho, polar radius. That's it. And so, as you can see, a polar angle, phi, coincides actually with the trigonometric angle. If you can imagine this unit circle here, you realize that, oh, it's exactly a geometrical angle. This is why you can measure it from 0 to 2 pi. Or maybe, if you prefer, you can use from minus pi to pi. It doesn't matter, actually. It doesn't matter so much. Okay, what about polar radius? Polar radius, it has a limitation that it cannot be negative, of course. Any distance should be positive or at least equal to 0. It cannot be negative. So these are limitations for these polar coordinates. What else? You need, but you know what? Our problem will be to make this transition into polar coordinate in some effective way. The convention is to give you all the curves in the Cartesian coordinate system. And if you're, especially if you're given a circle, we realize that we need uh, find a simpler method for circles. We realized it just from previous section. So what are these formulas which allow you to do this transition? We can call them transition formulas, and they show us the relationship between Cartesian coordinates x and y and polar coordinates. And it turns out this relationship is quite simple. Rho times cosine of phi, and y is equal to rho times sine of phi. So these are very famous transition formulas. Remember, I told you before, and I'm telling this again, that instead of letter R, which people prefer to use, I prefer to write rho because it looks much more explicit. My handwriting is very bad. Somehow I can't write properly this letter R. It always looks like 2 or something else. Okay, so we know now these wonderful formulas, and now it's time to practice. What exactly are we going to do now? We are going to convert curves given in coordinate in the Cartesian coordinate system into polar form. So let's start with, let's call it exercise 3, of course, exercise 3. And our first curve will be x squared plus y squared is equal to 4. The simplest curve possible. This is the circle with the center in the origin and radius being equal to 2 because it's 4, it's 2 squared. How to rewrite this equation in the polar coordinate system? You should use these formulas. Instead of x, you can plug in rho times cosine phi and so on. So let's do it. Instead of x, I'm plugging in this first expression, rho squared times cosine squared phi plus rho squared sine squared phi is equal to 4. Now it looks pretty daunting, but you need to simplify this. You can see on the left-hand side 2 terms, but they have a common factor, rho squared. Let's pull out rho squared, and you will be left with this expression inside, which looks pretty familiar to you, I hope. Yeah, that's right. This is the most famous formula from trigonometry. This expression is equal to 1. That is why our equation simplifies significantly all of a sudden. Rho squared is equal to 4, which means that rho equal, you might be tempted to write that plus minus minus 2, but let's write only 2 because we know this limitation, this limit, that rho cannot be negative. So look at this, it looks like a miracle. This equation of the circle didn't look very simple. It didn't look very simple in Cartesian coordinate system, but in the polar coordinate system, it looks amazingly simple. Just rho is equal to radius, and this fact actually can be generalized So we can make a conclusion that any circle of this form, x squared plus y squared is equal to radius squared, can be rewritten in the polar coordinate system just as a rho is equal to radius. Radius is a constant. So it's quite an amazing fact. You see that the equation of the circle simplifies dramatically, I would say. It looks really, really attractive now, especially when it comes to integrating. But let's do one more exercise. Exercise 5. Let's try and convert, for example, parabola into polar coordinate system. Y is equal to x squared. What happens to parabola? Is it going to get simplified or not? We are curious about this thing. Okay, let's substitute transition formula rho times sine of phi instead of y, and instead of x we substitute rho times cosine of phi. We will have rho squared cosine squared of phi. And now we can actually divide both sides by rho. We'll be left with sinus phi is equal to rho times cosine square phi. And finally, we can express rho from here. It will be left-hand side sinus phi divided by cosine squared of phi. So that's how like parabola looks in a polar coordinate system. What can we conclude looking at this equation? We can conclude that it doesn't look very simple. I would say that even looks much more difficult, much more involved in the polar coordinate system. So the conclusion is that any other curves apart from circles, they don't look very well in the polar coordinate system. And that is why if your region of integration for double integral consists of is built by conventional curves like parabolas, maybe straight lines, maybe it doesn't make sense to make this transition into polar coordinate system. Only when we are dealing with circles, it's really a great idea. But in any other cases, it doesn't look so impressive. It doesn't simplify things. On the contrary, I would say it makes things even more difficult. Okay, now I think it's time for you to practice this skill. I mean, converting curves into polar coordinate system. That is why here's your homework number 2. You can pause the video. As you can see, I gave you five very famous curves, and you are asked to convert them, these equations, convert them into polar coordinate system, just to get a sense of how it all looks like. Okay, so pause the video. After that, here are the answers to your problems. You can now have a look at them. And now we are ready to start talking about double integrals as well. So let's write it like a third topic, and let's call it double integrals in polar coordinate system. Double integrals in the polar coordinate system. In the polar coordinate system. Okay, I'm running out of space. It doesn't matter. Okay, so what do we have? So as usual, we are given double integral over some region D and from of some function f of xy dx dy. Double integrals are always written in Cartesian system of coordinate, and it's up to you to decide whether to stay in the Cartesian coordinate system or maybe make a transition to polar coordinate system. So the question arises is how should this standard template for region D should look like in a polar coordinate system. Let's consider this. So as you remember, our first template was the region which was squeezed between two vertical lines. Okay, the next template was the region which was squeezed between two horizontal lines. What our region is going to be squeezed in this polar coordinate system? It means that it turns out it will be squeezed between two arrows, between two rays coming from the pole, from origin, from the pole. This arrow has angle phi 1, and this arrow is angle phi 2. Angle means angle between the arrow, the ray itself, and this this x-axis. It's not called axis, it's called polar axis as far as I know, but it doesn't matter. Okay, what next? So squeezing of the region happens between two rays coming out from the source, coming out from the origin. So this is the difference. But as for boundaries, something looks pretty similar. So you have this boundary here, and you have this boundary here, So that's how your region looks like in a polar coordinate system. So this is region D. So this boundary has equation rho is equal to rho 2 of phi, and this region, red one, has equation, I need to show it with the rho is equal to rho 1 of phi. You know, before that we used words lower boundary and upper boundary. For the second template we used left boundary and the right boundary. Here we can use maybe words like closer boundary because it's closer to the origin, and farther boundary. Maybe this will be, all right. So closer boundary and farther boundary, meaning that in relation to the origin, or pole, we should use the pole. Okay, so you need to determine that your region, your concrete region in your concrete problem does satisfy these requirements. So it could be viewed as belonging to this type. And so what next? How this transition to repeated integral happens. Let's denote it as capital I again. So I'm going to write it here, this transition. Okay, so repeated integral starts with d phi, with the angle. The region is squeezed between two angles, phi 1, phi 2. That's why from phi 1, from phi 2. You can immediately see some similarities with our previous templates. Okay, what next? Next, your limits of integrations go from the smallest limit, which is the closest boundary. Should be here, and here you should write the equation of the farthest boundary, which is in green. That's almost it. And you know what? Here I'm going to write quite a daunting expression now, but let's write it first and then discuss it. So rho times cosine of phi and r times sine of phi. Then r dr, and that's it. So we can put a frame around it. And now we need to discuss this expression a little bit because this guy looks especially scary. What does it mean, this expression? You know, it means that you were given function f of xy. You were given two variables, x and y. And as you make this transition into polar coordinate system, you are not allowed to have these letters x and y anymore under your integral. Look at this, no letters x and y, only phi and rho. And how to eliminate, how to get rid of these letters? You need to use these transition formulas, which I mentioned in the very beginning. So instead of x here, you substitute this transition formula for x. And instead of y here, you substitute this transition formula for y. You're just showing that I'm going to substitute instead of xy this expression. That's it. Okay, what about this r? It turns out that r is absolutely necessary. It's called Jacobian. When you make this transition from Cartesian coordinate system to the polar coordinate system, it turns out that so you used to have dx dy, and now instead of dx dy you write d phi d rho. It means that they are not quite equal each other unless you write this Jacobian. So I can write it somewhere here. So if you had dx dy, it should be equal to rho or r d phi dr. That's how it happens. So this is Jacobian. You should just write it just without thinking. Okay. So now we have a recipe, and now we need to get used to this region. This is super important, of course, as you may imagine. But how can we use the template? Let's just consider the first example, and we will see how this happens. So it's going to be example 6, I suppose. Example 6. Here we have double integral as usual without function, or I mean with unknown function, f of xy dx dy, where the region is given by this equation, x squared plus y squared is equal to 4, but also, again, But also you are given these inequalities, x less than equal 0 and y is non-negative. So you can use all these, all these inequalities and qualities and equations to sketch your region. Okay, let's try and sketch this region first. So we immediately recognize that this is a circle, of course. This is a circle with the radius 2. So I'm going to draw it in a dashed line because maybe it won't be the whole circle. Yeah, that's right. Because x less than or equal to 0 it means that only the left half of the circle. And this equation means that only the half part. So we end up having only a quarter of the circle. So this is our region D finally. This is our region D. Okay, and what do we need to do now? We realize that our region is formed by a part of the circle. It means that it's better to make this transition into polar coordinate system because otherwise the integral will be very difficult anyway. So it's better to do it from the very beginning. But how can we see this template, in our concrete region? They already don't look very similar. So maybe we should use, the next technique. Our region, this standard region, should look like maybe like a piece of cake. Can you imagine that there was a cake, not around it, with this boundary? This is the upper boundary of the cake, and you decided to cut out the piece for yourself. And of course, and also there was a other boundary. Maybe someone has eaten part of the cake here. So it's like a piece of cake. So you can see, you should be able to see this piece of cake, in this region. Of course, this particular region, this is just the first example, is not particularly difficult. You can explicitly see the cake, and you cut out only the quarter of the cake. But nevertheless, it's a good start. It's a good start. So how can we start writing this repeated integral? So the first integral should be d phi. You need to decide upon the angle between which rays your region is squeezed. It's pretty obvious that it's squeezed between this ray and between this ray. This ray has angle pi over 2, of course, and this is pi. You should always use this direction anti-clockwise, counterclockwise. So from pi over 2 to pi. Okay, we finished our first step quite successfully. What about the second one? How determine which boundary is green one, farthest boundary, and which is the closest boundary? This looks a little bit more difficult. You know what? You can use the method of so-called sweeping rays. You can imagine that, sweeping rays, you can imagine the image, you can exploit the image of, what is the name of this thing? Screen swipers, uh, so you can imagine that you use this ray starting from this position, and you start moving, and as a result, you sweep the whole region. You sweep the whole region here. And to decide how you change your angle, it's very easy. We could use the sweeping angles as well. So this is the starting position of the sweeping ray, and this is the end position. That's how we determined our angles, but it wasn't very difficult. But now the time comes for these boundaries, and this is where difficult comes. Look at this. Look at one of these sweeping rays like under microscope. When the ray enters our region of interest, it always starts on this red curve, and it always finishes. And then when this ray leaves the region, it always happens on the farthest boundary, on the green line. So this is why, that's how we can determine. So let's look at one particular ray here, sweeping ray. It all starts here, at the origin. And when it leaves the region, so it goes this way, like from the source, and it always leaves the region on this curve. So it means that this circle is our farthest boundary. And as for the closest boundary, it's just the origin. It's just one point which corresponds to r is equal to 0. So our integral goes from 0. But what about this? What about this farthest boundary? We need to rewrite the equation of our circle in the polar coordinate system. But maybe you remember, we already made this wonderful conclusion. It could be written like r is equal to radius, which is 2. So it's just r equal to 2. So let me write it somewhere here. The equation of our circle looks very, very simple in polar coordinate system. So it will be from 0 to 2. And then, you know, I'm not gonna write all these details here. So just rho, the rho. Rho is Jacobian of our transition. So our first example was quite successful, but I think that we need more. Let's try to do the whole circle. The next example will be very easy as well. So example 7. So again, we are given a double integral as usual with unknown function. Let me write it here. Maybe it's not even necessary to rewrite it all the time, but okay, let it be. And so this time our region is bounded by the whole circle without any limitation. So the whole region inside this circle. This is even simpler than the previous case. It's the whole cake. If you want to use the term cake, it means that you are not cutting out anything of this cake. You are eating the whole cake. So what about our angle? Let's just use sweeping rays. So you start from 0 and you start turning this ray until you sweep the whole region. Your ray will turn the whole circle from 0, which means from 0 to 2 pi. Next, what about next one? We already have some experience. We need to look at each ray under microscope maybe. So let's have a look at this ray under microscope. It starts just like in the previous case. It starts in origin, in pole. It means rho is equal to 0 again, just like in previous case. But as for the farthest boundary from the origin, all these rays leave our region on this curve. And we know the equation of this curve is rho r is equal to 5. Radius is 5. So from 0 to 5. And again, I'm rewriting this function a little bit carelessly because I don't want to write all this terrible expression. R dr. That's it. So these were two quite easy example, quite simple example. Let's try to do something more interesting. So it's going to be example 8. And it's going to be a circle again. We realize that it makes sense to deal with polar coordinate system when you're dealing with circles. But this time, circle will be a little bit more interesting. So our region D is x minus 2 squared plus y squared less or equal than 4. Sometimes I am writing region in the form of inequalities. Okay, what is this? What is this circle? This circle has a shifted center. So the center of the circle is in the point 2, 0. 2, 0. Yeah, so let's write it. So 2, 0. And the radius is 2 as well. So this circle looks like this. 4. So our region D is everything which is inside this circle. So how should we go about this region? We need to be able to see the piece of cake in this region, and this looks pretty difficult, you know, to be honest. But let's try to do it anyway. The only method which will rescue us will be this method of sweeping rays. But let's start writing. I forgot to write that we were given double integral. So this is given double integral, and we need to rewrite it in the polar coordinate system. Well, so we start with d-phi, but even d-phi doesn't look very simple here. You know why? Because we need to use these sweeping rays, or let's draw them in yellow. So sweeping rays always start in the origin or in the pole, and they go like this, and this. So they make all this way from here to here. What do you think? What is the starting position of your ray? It's minus pi over 4. This is a vertical position because that's how the tangent to this line, to this circle looks like. And then you turn the sweeping rays until it becomes vertical again. So the finishing position is this one. So this is from minus pi over 2 to plus pi over 2, or minus 90 degrees plus 90 degrees. So that's how you should be able to determine the limits for phi. As you can see, in some cases it's not so easy. You need to really get used to it. Okay, what about closer and further boundary? So I'm rewriting this from the very beginning, this Jacobian and everything. Okay, let's have a look at one concrete sweeping ray under microscope. So as you can see, just like in the two previous cases, it starts from the origin, so we can write r is equal to 0 here. But what about the curve where this super ray leaves our region? It all happens on the whole circle, by the way. If you look at every row, you realize that they all leave our region on this circle. It means that this circle, even though it looks very strange, very weird, but nevertheless it plays the role of this farthest boundary, which I denoted in green. So it means that we need to rewrite this circle in the polar coordinate system, and it will require quite a lot of space actually. So let's do it here. So here's my circle in Cartesian form. Now, to transform this equation into polar coordinate system, I need to substitute these transition formulas. So instead of x, I substitute r cosine of phi minus 2 squared plus, instead of y, I substitute r sinus phi is equal to 4. As you can see, the resulting equation is quite big, a little bit daunting, but we have no option. We need to simplify it. I suggest we should do this multiplication. So it will give us r squared cosine squared of phi minus 4r cosine of phi plus 4. And I rewrite this term. R squared sine squared of phi is equal to 4. Looks even worse. But you know what? The good news is that these two terms cancel out, and moreover, we can consider these two terms and realize that if you pull out the common factor r squared from these two terms only, you will end up having 1 inside the parentheses. Let's do it. So cosine squared 2 plus sine squared of phi. But as for this term, let's move it to the right hand side. 4r cosine of phi. And so what do we have? You recognize this expression again. It's just 1. So the left hand side turned into r squared. So let me move somewhere here. So r squared is equal to 4r cosine of phi. And now, finally, we can divide both sides by r. R is equal to 4 cosine of phi. Very interesting. So that's how the equation of this shifted circle looks like in the polar coordinate system. Definitely much better than in Cartesian coordinate system. Maybe it's not as easy as this one most beautiful circle, but nevertheless it's quite good. So we can write it here as the upper limit of integration, 4 cosine of phi. So this was example 8. And you know what? I decided to, I have even 2 more examples for you. Okay, let's go over these examples. They are all very, very useful. So example 9, next one. Example 9. Example 9. So again, you are given double integral and you are given region, another circle. X squared plus y minus 1 squared is equal to 1. Let's consider this circle. Again, this is another shifted circle with the center being in 0, 1, center 0, 1. So it's shifted along a y-axis. And so this circle looks like this. Here's 1, here's 2, radius is 1. So this is our region. Our region is entirely inside this circle. And again, the assignment, our assignment is the same. We are given this double integral, and we are asked to rewrite it in a polar coordinate system. So we need to start with d phi and then write something else here. Okay, as you realized as you understood from the previous example, it's better to use sweeping rays because otherwise sometimes it's absolutely impossible to see the piece of cake behind this beautiful region. Okay, let's start sweeping our region. So we start with 0. You already know from the previous example that it's better to start with tangent line. And we're sweeping our region, and we stop here, pi, 180 degrees. So our angle turns from 0 to pi. Now, to determine these closest and farthest boundaries of our region, we need to look at every row like under microscope, as I said before. And you realize that all the rows, just like in the whole previous example, they start from the origin, which means that I is equal to 0 is the equation of our origin. But as for the farthest boundary, this is the whole circle again, So we are going to write the equation of the whole circle, but first we need to transform it into polar coordinate system. And I'm going to do it here, but I'm going to do it in less detail than before. So again, just like in all previous cases, you need to substitute these transition formulas instead of x and y. Sine of phi minus 1 is equal to 1. But you know what? I'm not going to show you all these workings. I think that you can easily do it yourself. I leave it for you as a homework. I'm only writing you the result. The result will be rho or r is equal to 2 sinus phi. That's it. So this is the equation of my green circle. And this serves as the upper limit of integration. We put it here. And as for the rest of the expression, we're just rewriting it and not forgetting about Jacobian. So that's it. But you know what? What was bad about all this example which I just gave you, that every time our closest boundary was 0, was actually our origin. You might get the wrong impression that it's always the case. No. That is why, let me give you one more example. Example 10. Example 10 will be the region D, which is formed by two circles. So x plus 1 squared, x plus 1 squared plus y squared is equal to 1. And there is another circle, x plus 2 squared plus y squared is equal to 4. So the region is between two circles. You can even put inequalities here. This inequality and this inequality. The first one means that the region which is outside the circle, and this inequality means that region which is outside, inside this circle. So outside of this circle, inside of this circle. But let me draw these circles first. These are actually shifted circles. That's why the picture promises to be quite interesting. So the first circle has a shifted center -1, 0. So it's here, and the radius is 1 as well. So -1, -2 will be here. The second circle has center -2 and radius 2. So it can be depicted something like this. Very interesting picture. Look at this. Very exciting. And the whole region is between these two circles. Between these two circles. Maybe it's not quite a nice idea. Yeah, nice idea. Okay, so, and our task is the usual one. We are given double integral as usual, double integral, and now we need to rewrite it in a polar coordinate system. So we realize this themselves because there's no way we can calculate this integral in the Cartesian coordinate system because it involves too many square roots. Okay, let's start using our sweeping rays. So sweeping ray, sweeping ray, sweeping ray. Of course, you realize that your sweeping ray starts with pi over 2, 90 degrees. This is pi divided by 2. And you travel this way, travel, sweeping, and you end up in this position, which corresponds to angle 3 pi over 2. So from pi over 2 to 3 pi over 2. So we are done with the angle. What about closer boundary and the farthest boundary? Now let's have a look at one of these rays. So this ray starts, every ray always starts in the origin, but it has nothing to do with our region. This is, empty region here. But the ray starts here, and it starts traveling and bumps into our region. So it all starts on this curve. So this curve, this small circle, serves as a closest boundary, closest to the origin. Let's look at this ray again. So it hit the region along the red curve. It travels inside the region, and then it leaves the region, and it always leaves the region, along this green curve. So we know that the closer circle serves the role of the closer boundary. So this equation should be put here, and I leave it to you to make sure that to transform these equations into polar coordinate system. I'm going to write you only the answers. You can pause the video and try to do these calculations by yourself. So the first equation looks like minus 2 cosine of phi. So this is the equation of the smallest circle. And the biggest circle should have equation minus 4 cosine of phi. So as I said before, just pause the video and try to make sure that I have made any mistakes. So that I haven't given you the wrong information. So that's how it looks like. Okay, so now you do get the idea of how to make this transition into polar coordinate system. And before trying to solve some problems from your tutorial sheet, I suggest you should do another little homework. So this is the homework for you, where you asked the similar thing to what I've just done for you by this showing you these 5 examples. I'm giving you 3 examples, and your assignment is to make this transition into polar coordinate system. So you need to transform double integral into repeated integral written in polar coordinate system. Okay, so pause the video, try to solve these tasks, these problems, and here are the answers for you. The answers, I even plotted the curves, the regions for you. So look at these answers. And now we are ready. We are ready for our last topic, just solving problems. So topic number 4, solving problems from our tutorial sheet. Solving problems from tutorial 9. It's actually only one question there, question 1, but it has many sub-questions. So I'm going to go over only 2 of them now, and I'll leave the rest as a good homework for you. Okay, so the first one will be question 1a. Question 1a. In this question, you are not given a double integral, you are given a repeated integral. So let's copy this repeated integral. So it looks like this, from 0 to 1. Here you have from 0 to square root of 1 minus x squared. And you're given concrete function at last, 3x plus 2y squared and dy dx. And you are asked to calculate this integral by transforming it first into polar coordinate system. But you know what? You don't even need these instructions. You should realize it yourself that as you can see this square root, there's no way of calculating this integral. You know, it usually turns into something really difficult. That is why it's an absolute necessity to turn this integral into polar coordinate system. But first of all, we need to restore the region which is hiding behind all these integrals. You know, to do this, I think that it's better to put parentheses around this internal integral. And maybe it's better to rewrite it in our favorite form. I prefer to move dx in front. So let's do it. Maybe I don't have enough space here, but I'll try to squeeze it here. So this is our first integral dx, external integral, of course. And this is, I'm copying the internal integral here. This looks much more convenient. Okay, so looking at this repeated integral, it realized that it starts with the x, and that is why this region is squeezed between 2 vertical lines. So let's start with these 2 vertical lines. So this is our coordinate system, and 2 vertical lines are 0, which coincides with this y-axis. 0 and 1 is here. So this is was our good start. So this is our actually lower boundary. So it could be interpreted as y is equal to 0. So y is equal to 0 is this one. Y is equal to 0. What about the upper boundary? Upper boundary is represented by this equation, but it doesn't look very beautiful, this equation, I'm afraid. Let's rewrite this equation here and start to figure out what is this equation, what is this curve which hiding behind this equation. It doesn't look very beautiful. You know what? We need to rewrite this equation in some other form, because it looks you can't just recognize. So I think that a good idea is to take a square or to square both sides of this equation. And after that, you can move x squared to the left-hand side and leave with, and we immediately guess. It turns out that it was a circle, but not the whole circle, but only half of the circle. You know why? Because if you were given this circle, this equation, and you were asked to express y in terms of x, you would obtain this expression, this plus and minus in front of square root. But in your case, only plus was given. And you remember from the beginning of this tutorial, the plus sign corresponds only to the top half of the circle. So what can we do? We can actually, the circle with the radius 1 and the center in 0. So I can draw the whole circle first. So this was the whole circle. But we need the part which is inside this, between these vertical lines, and also only upper part. So we ended up having this one. So this is our region. We managed to restore our region. Okay. So it's a piece of cake, actually. It's the quarter of the cake. And now, of course, we need to make this transition into polar coordinate system. Okay, so let's do it. Unfortunately, I'm out of space. So maybe I copy my integral here, actually, my repeated integral here on this new page. I'm just copying it here. So 0, we had this expression here, 3x plus 2y squared dy. Okay, now we need to look at the region. So we can use our favorite sweeping arrows, of course, even though the region is super easy compared to what we've done before. But nevertheless, you can see that your angle rotates from 0 to pi over 2. So this is our first integral, d phi, from 0 to p over 2. Okay, what about the next integral? The next integral is even easier. So as in many previous examples, your superray starts in origin, which means this lower limit of integration is 0 again, like in the majority of cases. And this, the green one, is the farthest boundary. And farthest boundary luckily have quite a wonderful, quite a beautiful equation. So this is the most beautiful circle of all. Rho or r is equal to radius 1. So our upper limit will be just 1. Okay, but now we have a difference. We have a use. So we are given a concrete function. Before that, I used to write f of xy, but now we have a concrete function. It means that we need to turn these guys, x and y, into phi and rho only. And to do this, you need to take the same course of action as before. Instead of x, we substitute this transition formula, rho cosine of phi. And instead of y, you substitute its own formula, rho squared sine squared of phi, parentheses are closing, and r dr. Don't forget about this Jacobian r. And now let's calculate this integral. I'm absolutely determined to do it at least once during this tutorial. Okay, it looks pretty daunting, this expression, but nevertheless, it's given in your tutorial sheet. It means that you should be able to do this integration. I think the best idea is to do this calculation because you can see rho, r or rho here. That is why let's multiply this expression by rho. So I need to rewrite the first integral, d phi from 0 to p over 2, integral of 0 to 1. I prefer to use brackets, as you notice probably. So it will be 3 rho r, let's call it r squared cosine of phi, plus 2 r cubed sine squared of phi. Brackets are closing, dr. Okay, so and let's be very concentrated. So I'm starting integration. So the first integration should be done with respect to r. It means that phi and cosine of phi turn into constants, for example. It means that the only variable is r squared here, and as for 3 times cosine of phi, it could be rewritten. It remains there. And the antiderivative of r squared is r cubed divided by 3. And I'm rewriting this vertical bar with limits, 0, 1, plus. What about the second term? The same thing happens here. 2 times sine squared of 5. It's like a coefficient which remains there. And the only thing which makes sense here is r cubed. The antiderivative is r to the power 4 divided by 4 and with these limits of integration. Now we need to substitute these limits of integration instead of r, of course. But you know it's super easy. When you substitute 1, it turns into 1, and 0 turns everything into 0. So we'll have 3 cosine of phi. That's all what is left from the first term. And something similar happens here. We can actually simplify 2 and 4. It will be 1 divided by 2. And here you have sine squared of phi, and that's it, because this guy turns into 1. So now we have quite an ordinary, quite a conventional integral. If you feel uncomfortable about this dphi, you can move it to the right. You can move it to the right. But now we need to discuss how to deal with two integrals. The first integral is actually a very simple one. It's like a table integral. But the second one, it's a little bit more interesting. That is why I suggest we split this integral into two terms, or is equal to first integral will be 3 cosine phi d phi. And the second integral will be like a second term. So because we need to discuss them separately. And let's denote them as I1 and will be I2. So our sum will be I1 and I2. And I'm going to discuss them separately, one by one. So let's consider the first integral. I1, I'm copying it here. It's integral of 0 from 0 to pi over 2, 3 cosine of phi d phi. It's just like a table integral, just standard integral. 3 is coefficient, and integral of cosine of phi is just sine of phi from 0 to pi over 2. And so you need to substitute these limits instead of phi. So it will be sine of pi over 2 minus sine of 0. And you should know the sine of 90 degrees is 1 and sine of 0 is 0. So our answer is 3 for the first term. So let's move to the second term, which is here. I'm copying it here. 1 over 2 in front of the integral. 0 to p over 2 sine squared of phi d phi. How would you deal with this integral? It turns out that in trigonometry there are two quite nice formulas. So sine squared of phi is equal actually to 1 minus cosine of 2 phi divided by 2. And there is a similar formula for cosine squared of phi. Just write it down just in case. Maybe you will need it maybe on your exam or somewhere. So and the idea is to use one of the formulas, the first one to be exact, to simplify this expression. Not to simplify, but to make it, more integrable. So what can we do? Let's substitute this formula. Let's apply this formula to this sine squared. So 1 minus cosine of 2 phi divided by 2. I'll put parentheses. And again, this is a good idea to split this integral into the sum of two integrals. It will be 1 over 4, 0 from 2 to d phi, and minus 1 over 4, integral of 0 to pi over 2, cosine of 2 phi d phi. So the first integral is super easy. Integral, it looks like integral from nothing. It's actually not nothing. There is a function 1 here, but it is a convention among mathematicians not to write this 1. So it's just phi. So it will be 1 over 4 phi with vertical bar from 0 to pi over 2. What about this integral? And in this integral, you should remember, it rather looks like the first integral. The integral of cosine was just sinus phi. But what about cosine of 2 phi? You should remember that in this case, you should bring out 1 over 2. And after that, you can write that this is sine of 2 phi with vertical bar from 0 to pi over 2. And finally, we have here 1/4 times pi over 2 will be pi divided by 8. Here we have 1 divided 1 by 8, and here you have sine of pi minus sine of 0. But you know what? Both sine of pi and sine of 0 are zeros. That is why the whole term turns into 0, and you are left only with this pi over 8. Let's see. It's not it. Because you remember that our problem turned out to be quite a long one. I split the whole integral into sum of those two integrals. So our answer will be I1 plus I2, which is the sum of these integrals. So answer, I prefer to read it in the same page, will be y1 plus y2, which is 3 plus pi divided by 8. So this is the answer to this question 1a. Question 1a. So as you can see, the process of integration was a little bit long, but as for transition from Cartesian to polar coordinate system, it didn't pose any difficulty for us. And the only interesting problem among these, given in question 1, is actually question 1d. So what I'm going to do now, I'm going to start, writing this question 1d. But, it's not my intention to solve the whole problem. I'll leave it to you as a homework. I was just attracted to this problem because it seems to be the most difficult out of all of them. So again, you are given repeated integral from 0 to 2, and here you have quite fancy boundaries, minus square root of 4 minus x squared, and the upper boundary, it looks even fancier, 2x minus x squared, and all this. And here you have function x squared minus y squared dy dx. These square roots look pretty daunting, to be honest. Okay, so let's rewrite in the first place. Let's rewrite our repeated integral moving dx in front, because that's how we used to deal with repeated integrals. And I need to copy all this here, but it's not a big problem. I can copy them here. So our first task is determine the region of integration. Again, just like in the previous case, you can see that this repeated integral starts with dx. It means that we need to squeeze our region between two vertical lines, 0 and 2. So let's start doing this. So this is my coordinate system, x and y. And I start by plotting these two vertical lines. This is x is equal to 0, and this is x is equal to 2. X is equal to 2. So my future region of the integration will be squeezed between these two lines. Okay, let's start with the lower boundary. So lower boundary is this one. Y is equal to minus square root of this expression. Again, we already have some experience of dealing with this expression, and you might start suspecting that maybe this is a circle which is hiding behind this equation. To make sure that we guessed it right, let's just square both sides. This minus will disappear, of course. And let's move x squared to the left. And of course, indeed, it is a circle with the center in the origin, and there is a radius 2. So I can draw the whole circle in a dashed line. Like this. That's right. But what part of this circle I need? I need the lower part, the bottom half of this circle, which corresponds to here, and at the same time, only this segment which is inside this, inside these two yellow lines. So finally, I have only this one. So this is our lower boundary. Okay, now we know that this expression, upper limit, represents the upper boundary. So it's y is equal to this expression. We copied it from here to x minus x squared. So probably it's another circle, but who knows? We need to manipulate this equation. We need to simplify it. So let's square both sides as usual. Y squared is equal to 2x minus x squared. And let's move both terms into the left hand side. But you know what? This time it looks like we are in trouble. It doesn't look like equation at all. But you know what? We can consider these two x's, and we realize that if it looks like we are missing one term only to make this expression a perfect square. Indeed, if you add one to both sides of this equation, to the left hand and to the right hand side, and if you have a look at this group of terms like one entity, you realize that, this is a perfect square, and I can rewrite this equation, this expression as x minus 1 squared, and just copy the rest. So it's another circle, but it was difficult because it has this circle had origin center a little bit shifted. The center of the circle is 1, 0. So this is the center of this circle and the radius of 1. So if you want to depict the whole circle, it looks like this. But we are not interested in the whole circle because we realize that y was expressed in terms of x, and there was a plus sign in front of square root. It means that we need only the top half of the circle, which corresponds to this line. Okay, as you can see, very interesting task. And as a result, we do have region D. So region D is here between these two yellow vertical lines as usual, and with these two circles serving as upper and lower boundary. But how to make now? We are faced with another challenge. We need to rewrite this circle in the polar coordinate system. And of course, as usual, we try to use our sweeping rays. But you know what? The bad news, another challenge here. So let's try and draw these sweeping rays. Look at this. Once you travel from minus 90 degrees, minus pi over 2 to 0, the role of the further boundary belongs to this red circle. But once you uh, enter this upper region, you see that something changed. The role of this farthest boundary belongs to this green circle. It means that our region doesn't satisfy this standard template. We need to cut this region into two parts, just like in one previous example in the previous tutorial. So this will be our region D1, and this will be our region D2. And you will remember this property if you're of double integral. If your region of integration uh, can be represented as a union of two regions, uh, then your integrals get split into the sum of two terms, to the sum of two repeated integrals. So you can see that this is quite a challenging problem. It's the most difficult one out of many in question 1. So let's do it. So let me denote this integral as capital I, because it's quite a hassle to rewrite it all the time. So our integral I will be written at the sum of two repeated integrals, each of which is written in polar coordinate system. So let's keep this inside our region. So let's start writing along the first region D1. You can see that the angle changes from minus 90 degrees to 0 if you move your sweeping ray like this. So from minus pi over 2 to 0. This is D phi. Okay, the next one from 0. So the closest boundary is 0. It's not boundary, it's the origin itself, like in many previous cases. And the role of a farthest boundary plays this curve, this circle, which has a very nice equation in polar coordinate system. R is equal to radius, and radius was 2. So this is just 2. And here we need to rewrite our function, x squared minus y squared. So x squared will be r squared cosine squared of phi. X squared will be r squared sine squared of phi. And I shouldn't forget about Jacobian r plus. So this was the first term, the integral written over the first region D1. Let's move to the next region. In the next region, your sweeping ray changes from position corresponding to phi is equal to 0 to phi is equal to pi over 2. Pi over 2 d phi. Okay, and the next move is to have a closer look at each ray to realize where it starts. It starts in the origin again, so I wrote 0 here. We encountered this case so many times today. And as for the role of the farthest boundary, it belongs to the green curve now, which corresponds to this shifted small circle. And I leave it to you to transform this equation of this circle into polar coordinate system. I'm just writing you the result immediately. So the equation of this circle should be 2 cosine phi. Maybe it's better to write it in green, otherwise you might get lost probably. So I leave it to you as a little homework, just pause the video and try to obtain this equation by yourself. And again, this function should be written in the same way, and so on and so on. And I'm not going to calculate this integral because it's quite a long story. If you're interested, you can do it yourself. And the integrals are quite long, it requires too much time. I think that's enough for you. So that's it. So that's it for today.